Tonight, we're going to look gently at something that might quietly reshape the way you think about doing absolutely nothing. Right now, as you rest here listening, you are, in a very real sense, in the middle of an extraordinary journey through space. You're moving at more than 1,000,000 miles an hour. And it begins with something small, the Earth, turning beneath you. The turning Earth is circling the Sun. The Sun, in turn, is sweeping around the galaxy, and the galaxy itself is drifting through the wider cosmos. Each of these motions stacks on top of the last, all of them happening in this very moment, each layer quietly adding its own speed to the one before it. By the time we reach the end of tonight's journey, you'll understand each of these hidden layers of movement, you'll see clearly why none of it can be felt, and you'll discover, quietly, where all of this motion is actually carrying us. Before we drift any further, if you enjoy wandering through the mysteries of space as much as we do here, it would mean a great deal if you took a moment to like this video or subscribe. It costs nothing but a second, and it helps this little corner of the internet reach more curious minds like yours. Now, let's begin. Let's start with something very simple. Wherever you happen to be right now, everything probably feels calm. Nothing seems to be moving. The room feels steady, still, unshaken, and that matches exactly what your senses are telling you. But your senses, as reliable as they feel, are only showing you a small slice of the truth. They were built to notice motion relative to what's nearby, not motion in any absolute sense. They compare you to your immediate surroundings, and nothing more. So if everything around you happens to be moving at the very same speed you are, your senses simply register calm, silence, stillness, which means, in principle, you could be traveling at almost any speed imaginable, and as long as your surroundings traveled right along with you, it would still feel like nothing at all was happening. And that, as it turns out, is precisely our situation. The Earth is moving, astonishingly fast. Let's walk through just how fast, one gentle layer at a time. The first layer of motion is the one most people have at least heard of. Earth spins on its axis, turning like a slow, massive top, completing one full rotation every 23 hours, 56 minutes and 4 seconds. Astronomers call this a sidereal day. It's a little shorter than the familiar 24-hour day we set our clocks by, because Earth is also travelling around the Sun at the same time. And that orbital motion adds a few extra minutes before the Sun lines up in the sky again the way it did the day before. But let's stay with the spinning itself for a moment. The circumference of Earth's equator comes out to roughly 24,901 miles, and that whole distance gets covered in a single rotation. So if you happen to be standing right on the equator, you're moving at about 0.40 miles an hour. That's faster than the speed of sound, which travels through air at sea level at around 767 miles an hour. Right now, if you're near the equator, you are moving faster than sound itself, and you can't feel even a trace of it. Of course, most people don't live on the equator, and the speed of Earth's spin depends heavily on how far you are from it. The farther from the equator you go, the slower your personal spin becomes. Someone in New York City, sitting around 40 degrees north, is moving at roughly 794 miles an hour. Someone in London, near 51 degrees north, is moving at about 650 miles an hour. And if you happen to be standing right at the North or South Pole, You'd barely be moving at all from the spin, just slowly turning in place once every day, like the very center of a record. But no matter where you stand on this planet, you never feel the motion. Why is that? Because everything around you, the air, the ground, the buildings, your own body is spinning along with you at exactly the same rate. There's no difference in speed between you and your surroundings, so your senses have nothing to latch onto. That's the first layer. Earth spinning quietly on its axis. And we've barely started. Now let's talk about the second layer, the Earth's long orbit around the Sun, and this one moves considerably faster. On average, Earth sits about 93 million miles from the Sun, a distance we call 1 astronomical unit. The path Earth traces is almost a perfect circle, though it's actually a very gentle ellipse. Over the course of one full lap, Earth covers roughly 584 million miles, and it does this once every year, or about 365.25 days. So how fast does that make us? Divide 584 million miles by 365, 25 days, and you get roughly 1.6 million miles covered every single day. Divide that by 24 and you land on about 66,600 miles an hour. That's Earth's orbital speed around the Sun. To put that number in perspective, the fastest jet aircraft ever built, the Lockheed SR-71 Blackbird, topped out around 2,193 miles an hour. Earth is coasting through space roughly 30 times faster than that. Even the fastest spacecraft humanity has ever launched, the Parker Solar Probe, only reached about 430,000 miles an hour at its closest pass by the Sun, faster than Earth's orbit. Yes, but not by nearly as wide a margin as you might expect. We're talking about an entire planet, a colossal ball of rock and metal weighing something like 6 sextillion tons, sailing through the void at well over 66,000 miles an hour. Every single second, Earth advances about 18.5 miles along its path. In roughly the time it takes to read this sentence, Earth has already carried you dozens of miles further through space. And once again you feel none of it. Because you're moving together with Earth, the atmosphere moves with it. The ground moves with it. Everything on the surface travels as one. There's no wind from this motion, because the air is keeping perfect pace with the ground beneath it. There's no sensation of speed at all, because nothing in your immediate frame of reference is moving any differently than you are. This touches on one of the deeper truths of physics. If you were sealed inside a windowless room, moving in a straight line at a perfectly steady speed, there would be no experiment, no test, nothing at all you could do inside that room to figure out how fast you were going. This is the principle of relativity, first glimpsed by Galileo and later refined more deeply by Einstein. Motion, it turns out, is relative. The only thing you can ever truly detect is a change in motion acceleration. As long as Earth keeps its orbital pace steady without speeding up or slowing down, there's nothing for your body to notice. Except Earth's orbit isn't perfectly steady. Because the orbit is a slight ellipse, Earth actually picks up a bit of extra speed in early January when it swings closer to the Sun, reaching about 67,600 miles an hour. And it eases off a little in early July when it's farther out, slowing to roughly 65,600 miles an hour. That's a difference of only about 2,000 miles an hour spread across 6 full months, so gradual a shift that no living thing could ever sense it. And yet it's there, quietly happening all the same. So that's the second layer Earth circling the Sun at more than 66,000 miles an hour. And we're only just getting started. Let's widen our view a little further, because Earth isn't the only thing on the move. The Sun itself is traveling, carried along its own path around the center of the Milky Way. Our entire solar system, every planet, every asteroid, every wandering comet is swept along with the Sun as it drifts through the galaxy. The Sun sits roughly 26,000 light-years from the galaxy center, a distance of about 153 quadrillion miles. It follows a nearly circular path around that center, though the precise shape is still being studied by astronomers today. One full circuit takes about 230 million years, a span of time we sometimes call a galactic year, or a cosmic year. The last time the Sun found itself in this exact position, dinosaurs were only just beginning to rise to dominance on Earth. By the time it completes its next full lap, our planet, assuming it's even still here, will look like an entirely different world. But let's focus on the raw speed for a moment. The Sun moves through the galaxy at roughly 490,000 miles an hour, nearly 500,000 miles every hour. To put that in context, it's about 220 times faster than Earth's spin at the equator and roughly 7 times faster than Earth's own orbit around the Sun. The Sun is racing through the galaxy, and it's dragging the entire solar system along for the ride, which means you, sitting quietly on Earth, are also moving at 490,000 miles an hour relative to the galaxy's center. Every second, the Sun covers about 136 miles. In the time it takes to blink, it has already carried you several miles further through the galaxy. And still you feel nothing, because everything in the solar system moves together as one unit. Earth travels with the Sun. The Moon travels with Earth. The other planets travel right alongside all of it. There's no wind, no drag, no resistance, because the space between the stars is almost entirely empty. The scattered gas and dust out there is so thin it creates no noticeable friction at all. Here's something worth pausing on, though. The Sun isn't moving in a straight line, it's orbiting the galactic center, which means its direction is constantly, gently changing. And any change in direction, even without a change in speed, counts as acceleration. But the curve of the Sun's orbit is so vast, so gradual, that this acceleration is far too small to ever notice. The pull keeping the Sun on its galactic path is tiny compared to the pull of gravity you feel just standing on Earth's surface. So again, undetectable. That's the third layer, the Sun sweeping around the Milky Way at roughly 490,000 miles an hour. And we're still not finished. Now let's consider the motion of the Milky Way galaxy itself, because it isn't sitting still either, it's moving through space. And here things get a little more delicate, because the moment you ask how fast a galaxy is moving, you have to ask, moving relative to what? There's no fixed point anywhere in the universe, no cosmic landmark quietly holding still while everything else rushes past. Everything, everywhere, is in motion. So to talk meaningfully about the galaxy's motion, we need to choose a reference frame. And the most useful one turns out to be the cosmic microwave background. This faint glow, often shortened to the CMB, is the leftover radiation from the Big Bang itself, filling every corner of the universe. It's the oldest light we can observe, released about 380,000 years after the Big Bang, once the universe cooled enough for atoms to form and light to finally travel freely. The CMB looks almost perfectly uniform, no matter which direction you look. Almost, there's a very slight temperature difference between one side of the sky and the other. Something astronomers call a dipole anisotropy, one side just a touch warmer, the other just a touch cooler. The gap is tiny, only about 3.3 millikelvin, but it's measurable and it tells us something important. We are moving relative to the CMB. The warmer patch of sky marks the direction we're heading toward. Light from that direction gets compressed, or blue shifted, by our motion toward it, which makes it appear slightly warmer. The cooler patch marks the direction we're moving away from. Light from there gets stretched, or redshifted, making it appear a touch cooler. By carefully measuring this tiny temperature difference, scientists can calculate our speed relative to the CMB. And the number that comes out is about 1,342,000 miles an hour. That is the speed of the Milky Way itself sailing through space relative to the cosmic microwave background. 1.3 million miles an hour. Let that settle for a moment. You are moving at over 1 million miles an hour right now, not because you're aboard some spacecraft, not because you're strapped into a rocket, but simply because you happen to live on a planet, inside a solar system, inside a galaxy that is itself moving through the universe at extraordinary speed. Every second, the Milky Way covers about 373 miles relative to the CMB. Every minute, over 22,000 miles. Every hour, more than 1.3 million miles. In the time it takes you to sleep for 8 hours tonight, the Milky Way, and you along with it, will have traveled more than 10.7 million miles through space. And you won't have felt a single moment of it. Now here's where it becomes genuinely interesting. The Milky Way's motion relative to the CMB isn't some random drift in an arbitrary direction. The galaxy is being pulled, quite literally, by gravity drawn toward a region of space known as the Great Attractor. This gravitational anomaly sits roughly 150 million light-years away, somewhere in the direction of the constellations Hydra and Centaurus. It isn't a single object at all, but rather a colossal concentration of mass, quite possibly a supercluster of galaxies, exerting its pull on our galaxy and thousands of others nearby. The Milky Way is, in a sense, falling toward the Great Attractor. That word falling might sound strange, but it's exactly what gravitational motion is. When something orbits a body, it's falling toward it while moving sideways just fast enough to keep missing. When something isn't orbiting and is simply being pulled, it's just falling. The Milky Way is falling toward the Great Attractor at hundreds of miles every second. But even the Great Attractor isn't the final word. Beyond it lies an even vaster structure called the Shapley supercluster, roughly 400 million light-years away, itself pulling on the Great Attractor, which in turn pulls on us. And beyond that, still larger structures stretch across the cosmos, vast filaments of galaxies, cosmic walls hundreds of millions of light-years long. All of these structures move relative to one another. Some drift closer together, others drift apart, carried by the expansion of the universe itself. So when you try to work out the true speed of the Earth through space, you quickly run into a problem. You can't simply add these numbers together, because each layer of motion points in a different direction. Earth's spin is tilted relative to its orbital plane. Earth's orbit is carried by the Sun's motion through the galaxy. The galaxy's motion runs at yet another angle relative to the CMB. All of it happening at once, all of it pointing different ways. To find a true combined speed, you'd need vector addition, treating each motion as an arrow with both a direction and a length, and the math quickly becomes intricate. Still, we can sketch a rough picture. If you're standing at the equator at local noon, you're spinning with Earth at about 1,040 miles an hour. Earth is orbiting the Sun at 66,600 miles an hour. The Sun is circling the galaxy at 490,000 miles an hour. And the galaxy is moving relative to the CMB at 1,342,000 miles an hour. If all of these motions somehow pointed the same way, you'd be moving at more than 1.9 million miles an hour. But they don't line up like that. Earth's spin runs perpendicular to its orbit. The Sun's galactic path tilts at its own angle, and the galaxy's motion relative to the CMB runs off in yet another direction entirely. So your actual combined speed shifts depending on where you stand on Earth and what hour of the day it happens to be. But the essential point remains: you are moving at speeds well beyond 1 million miles an hour, and you can't feel even the smallest trace of it. So why can't we feel any of this? It comes down to a handful of principles from physics. First, motion at a constant velocity simply cannot be detected. If you're traveling in a straight line at a steady speed, there is no way to feel it. This is exactly why Earth's orbit goes unnoticed over short stretches of time. It moves in a nearly straight line at a nearly constant pace, and the curve is so gentle that the resulting acceleration is far too faint to register. Second, when everything around you shares your speed, there's simply no relative motion to detect. This explains Earth's rotation perfectly. The air spins with the planet, the ground spins, the buildings spin, your body spins. Nothing around you is moving any differently than you are, so your senses find nothing to grab onto. Third, and perhaps most importantly, the accelerations involved are almost impossibly small. The acceleration from Earth's rotation is only about 0.034 meters per second squared at the equator. Compare that to the pull of gravity at 9.8 meters per second squared, nearly 300 times stronger. Gravity simply drowns out the rotation entirely. The acceleration from Earth's orbit around the Sun is smaller still, about 0.006 meters per second squared, over 1,600 times weaker than gravity. And the acceleration from the Sun's slow arc around the galaxy is smaller yet again, roughly 2 times 10 to the negative 10th meters per second squared, so tiny it might as well be zero for any human being to perceive. So all these staggering speeds we've been describing produce accelerations far too gentle for our bodies to register. We're essentially blind to them. The only accelerations we ever notice are the ones strong enough to compete with gravity itself. When a car speeds up, you feel pressed back into your seat. That's an acceleration of 2 or 3 meters per second squared, roughly on par with gravity, which is exactly why you feel it. When an elevator starts to move, you feel briefly heavier or lighter, another detectable change. But the motion of Earth through space is smooth, steady, and utterly constant, which makes it something we simply cannot sense. There's one more piece to this puzzle, and it isn't about speed or acceleration at all, it's about the medium we're moving through. When a car moves through air, you feel the wind pressing against it. But Earth moves through something close to a perfect vacuum. Space isn't entirely empty. There are scattered particles of gas, flecks of dust, traces of cosmic radiation, but the density is so vanishingly low that any resistance is essentially negligible. Even at the tremendous speeds we've been discussing, the thin gas drifting between stars creates no noticeable drag whatsoever. There's no cosmic wind pushing back against Earth, nothing slowing us down, nothing at all to create a sensation of motion. We are moving through a void, and the void simply doesn't push back. Now let's turn to something quietly astonishing, the expansion of the universe itself. There's one more layer of motion we haven't touched yet, and it's the strangest of them all. The universe isn't just full of things moving through space. Space itself is stretching, and that stretching carries galaxies apart from one another. This isn't movement through space in the ordinary sense, it's the expansion of space itself, a fundamentally different kind of motion altogether. To picture this, imagine a balloon with a few dots drawn on its surface. As you blow air into the balloon, the dots drift apart from each other, but notice, they aren't actually crawling across the surface. The surface itself is stretching, carrying the dots along with it. That's essentially what's happening throughout the universe. Galaxies aren't racing away from each other through space. The space between them is expanding, gently pushing them apart. The farther apart two galaxies happen to be, the faster the space between them stretches. This relationship is captured in Hubble's law. The speed at which a galaxy recedes from us is proportional to its distance. The current value of the Hubble constant sits at roughly 46 miles per second for every megaparsec of distance, and a megaparsec works out to about 3.26 million light-years. So for every 3.26 million light-years separating us from another galaxy, its recession speed increases by roughly 46 miles per second. Let's put some numbers to this. A galaxy sitting 100 million light-years away recedes from us at about 1,400 miles per second, more than 5 million miles an hour. One that's 1 billion light-years distant recedes at roughly 14,000 miles per second, over 50 million miles an hour. And a galaxy 10 billion light-years away recedes at around 140,000 miles per second, more than 500 million miles an hour. And here's the remarkable part. Beyond a certain distance, the recession speed actually exceeds the speed of light. This doesn't break any laws of relativity. Nothing is physically moving faster than light through space. But space itself is under no such restriction, and it can expand faster than light allows. The boundary where recession speed matches light speed marks the edge of what we call the observable universe. Beyond that line, galaxies are receding so quickly that their light will simply never reach us. They lie forever beyond our cosmic horizon. The observable universe stretches out to a radius of about 46.5 billion light-years, the farthest distance from which light could possibly have reached us. Anything past that boundary is, quite simply, beyond our reach forever, its light being carried away faster than it could ever travel toward us. So when we discuss the Milky Way's motion relative to the cosmic microwave background, we're really only describing local motion. The expansion of space is happening everywhere, all at once between the Milky Way and other galaxies, and even very faintly within the Milky Way itself, though gravity here holds everything firmly together and keeps the galaxy from being torn apart. On small scales, gravity wins. On the largest scales, expansion wins, and that expansion is, remarkably, speeding up. This discovery came in the late 1990s through careful study of distant supernovae. Scientists had expected the expansion to be gradually slowing, pulled back by gravity. Instead, they found the opposite. The expansion was accelerating. The result was so surprising that it took years of double-checking before it was widely accepted. But the evidence held firm. The acceleration is being driven by something we call dark energy, though we still don't fully understand what it actually is. It might be an intrinsic property of space itself, or perhaps some field spread throughout the universe. Whatever it turns out to be, it accounts for roughly 68% of the total energy in the universe, and it's steadily pushing space apart. In the far, far future, billions of years from now, this acceleration will carry distant galaxies beyond our cosmic horizon entirely. They'll fade quietly from view. The observable universe will shrink, and eventually the only galaxy still visible will be the small handful bound to us by gravity in our local group. Everything else will have drifted away, carried off by the relentless stretching of space. But that lies billions of years ahead. For now, we can still look out at a vast universe full of galaxies, moving through it ourselves at extraordinary speed. Let's pause here and gently gather all these layers together. First, Earth's rotation about 1,040 miles an hour at the equator. Second, Earth's orbit around the Sun roughly 66,600 miles an hour. Third, the Sun's slow arc around the galaxy about 490,000 miles an hour. Fourth, the galaxy's motion relative to the cosmic microwave background around 1,342,000 miles an hour. And fifth, the expansion of space itself, quietly carrying distant galaxies away at speeds that only grow with distance. All of these motions are unfolding simultaneously. Right now, sitting perfectly still, you are somehow spinning with Earth, orbiting the Sun, circling the galactic center, falling toward the Great Attractor, moving relative to the cosmic microwave background, all while the space around you gently expands and you can't feel a single strand of it. This might be one of the most quietly profound realizations in all of science. Motion is relative. There is no absolute frame of reference anywhere in the universe, no cosmic grid marking who's moving and who's standing perfectly still. Everything is moving relative to something else. When you say you're sitting still, what you really mean is that you're still relative to the ground beneath you. But that ground is moving relative to Earth's center. Earth's center is moving relative to the Sun. The Sun is moving relative to the galaxy. And the galaxy is moving relative to the cosmic microwave background, which itself is simply a convenient frame we've chosen, not some deeper truth more fundamental than any other. In a very real sense, there's no such thing as absolute motion. Only motion relative to something. Which means the question, how fast am I really moving, doesn't actually have one single answer. It depends entirely on what you're measuring against. Relative to Earth, you're barely moving at all. Relative to the Sun, you're moving at tens of thousands of miles an hour. Relative to the galaxy, hundreds of thousands. Relative to the cosmic microwave background, over 1 million. And every single one of those answers is correct. They're simply measuring different things. So what does all this mean for space travel? If we're already moving this quickly, shouldn't that make interstellar journeys easier? Couldn't we simply leap off Earth and let that motion carry us somewhere new? Unfortunately, it doesn't work that way. Stepping off Earth doesn't strip away Earth's motion. You're still orbiting the Sun at 66,600 miles an hour, still sweeping through the galaxy with the rest of the solar system at 490,000 miles an hour. Earth's motion is your motion too. To travel to another planet, you don't need to cancel out Earth's absolute motion through the universe. You only need to account for the difference in motion between Earth and wherever you're headed. Take Mars, for instance. It orbits the Sun at about 54,000 miles an hour, while Earth orbits at roughly 66,600. When we send a spacecraft toward Mars, we aren't fighting against Earth's motion at all. We're simply nudging the spacecraft's own orbit around the Sun until it lines up with Mars's path. The spacecraft leaves Earth already moving at 66,600 miles an hour around the Sun. It doesn't start from a standstill. It's already living inside the solar system's shared reference frame. All the engines need to do is adjust that orbit, slightly speed up a touch to swing into a higher, slower path that reaches out to Mars's distance, then slow down again once it arrives to match Mars's own orbital pace. The fact that the Sun is barreling through the galaxy at hundreds of thousands of miles an hour is completely beside the point, because Mars is caught up in that same motion. They share a reference frame. This is exactly why mission planners think in terms of the solar system, not the galaxy, and certainly not the cosmic microwave background. Within the solar system, the Sun functions as essentially stationary, with the planets circling around it, and that's really all we need for navigation. Navigating in space is, at its heart, a question of reference frames. When you look up at Mars from Earth, its motion across the sky looks complicated. Part of that comes from Mars's own orbit, and part comes from Earth's motion changing our vantage point. Sometimes Mars even appears to drift backward, a phenomenon called retrograde motion, which happens when Earth, moving faster along its inner orbit, overtakes Mars from the inside. From our angle, Mars briefly seems to reverse course. Ancient skywatchers found this baffling and invented elaborate systems of circles within circles to explain it. But once you understand that both worlds are simply orbiting the Sun, retrograde motion becomes a simple matter of perspective. Planning an actual mission to Mars means accounting for all of this, predicting Mars's position months ahead of time, calculating a trajectory that arrives at exactly the right place at exactly the right moment, factoring in the gravitational tug of Earth, the Sun, Mars, and sometimes other planets, and planning course corrections along the way. It's a genuinely complex puzzle, but the entire calculation stays comfortably within the solar system's reference frame. The galaxy's own motion never even enters the equation. Now imagine trying to navigate toward another star entirely suddenly. The galaxy's motion becomes very relevant indeed. Other stars are drifting at their own speeds, in their own directions relative to the Sun. The nearest star system to us, Proxima Centauri, sits about 4.24 light-years away, roughly 25 trillion miles. Its motion relative to the Sun breaks down into two parts: radial velocity, its speed toward or away from us, measurable through the Doppler shift of its light, and proper motion, its drift across our line of sight, measurable by watching its position shift against the sky over time. Proxima Centauri's radial velocity comes to about 14 miles per second toward us, and its proper motion, when converted using its known distance, works out to roughly 12 miles per second sideways. Combine the two, and Proxima Centauri is moving at about 24 miles per second relative to the Sun, around 86,400 miles an hour. If we ever sent a spacecraft toward Proxima Centauri, we'd need to account for that motion, aiming not at where the star sits today, but at where it will actually be once we arrive. At today's spacecraft speed, such a journey would take tens of thousands of years. Voyager 1, the fastest human-made object ever to leave the solar system, travels at roughly 38,000 miles an hour relative to the Sun. At that pace, reaching Proxima Centauri would take more than 73,000 years, and by the time it got there, the star itself would have wandered elsewhere. Moving at about 24 miles every second, Proxima Centauri would cover roughly 55 billion miles over those 73,000 years, ending up more than twice as far from its current spot as it currently sits from the Sun. You couldn't simply aim at where it is now, you'd have to aim at where it will be, and account for the Sun's own motion relative to nearby stars as well, since, from Proxima Centauri's vantage point, the Sun is the one doing the moving. Your spacecraft would essentially be chasing a moving target while itself being flung along a curved path shaped by the gravity of everything it passes. The mathematics gets complicated fast. This is precisely why interstellar navigation is such a formidable challenge. It isn't just the distance, it's the fact that everything out there is drifting in different directions at different speeds, and once you've launched, there's no pulling over to check a map. You can make small corrections along the way, but fuel is limited, and you largely have to get your initial aim right. To make interstellar travel genuinely practical, we'd need to move much faster than we do now. One proposed mission, Breakthrough Starshot, imagines sending tiny light sail probes toward Proxima Centauri at around 20% of the speed of light, roughly 134 million miles an hour. At that speed, the journey would take about 20 years. But even moving that fast, we'd still have to account for the star's own drift. Proxima Centauri would shift by roughly 10 billion miles over those 2 decades, about the same distance as from the Sun to Neptune. You'd have to aim that far ahead of its current position, and you'd also have to account for the effects of relativity. At 20% of light speed, time dilation starts to become noticeable. Time aboard the probe would run about 2% slower than time back on Earth. A 20-year journey from Earth's perspective would feel like about 19.6 years to the travelers themselves. Not an enormous gap, but a measurable one. And if we ever manage to go faster still, these relativistic effects grow more dramatic. At 50% of light speed, time dilation reaches about 13%. At 90%, it passes 50%. At 99%, time aboard the spacecraft runs about 7 times slower than back home. There's also length contraction to consider at very high speeds. Distances along the direction of travel appear compressed. At 99% of light speed, the 24 light-year gap to Proxima Centauri would appear, from the spacecraft's own vantage point, to shrink to just 0.6 light-years. This isn't some trick of perception, it's a genuine physical effect, space itself appearing contracted in the direction of motion. From Earth's perspective, that journey at 99% light speed takes about 4.3 years. From the traveler's perspective, it takes only about 7 months, because both time and distance behave differently depending on your point of view. These are real, thoroughly confirmed effects, consequences of moving at speeds that brush up against the speed of light, and they make interstellar navigation more intricate still. Ordinary Newtonian physics simply won't do. You need Einstein's special relativity, accounting for time dilation, length contraction, and the way velocities combine at relativistic speeds. Interstellar space, it turns out, is anything but empty in terms of motion. It's filled with the individual paths of countless stars, each one following its own route through the galaxy, each with its own velocity relative to the galactic center and to its neighbors. Navigating through that landscape requires understanding not just our own motion, but the motion of everything we hope to reach precise measurements of stellar positions and velocities, powerful computation to project trajectories decades into the future, and technology we simply don't have yet to reach the necessary speeds. But it is possible, at least in principle. The laws of physics allow it. We just aren't there yet, technologically. Perhaps in a century, perhaps in 1,000 years. But if humanity continues forward, we'll likely work it out sending probes to distant stars, mapping the motions of nearby stellar systems, learning to navigate the galaxy itself. And all of it will hinge on understanding motion, on grasping that nothing in this universe truly sits still, and that to travel anywhere you have to account for all of it. There's another consequence of all this motion, and it shapes how we actually see the universe. Light traveling from distant objects is altered by motion in a few distinct ways. First, there's the familiar Doppler effect. When something moves toward you, its light waves get compressed, their wavelength shortened. We call this blue shift, since the light shifts toward the blue end of the spectrum. When something moves away, its light waves stretch out, their wavelength lengthened. This is redshift, shifting toward the red end. Astronomers use this effect constantly to measure how fast stars and galaxies are moving toward or away from us, simply by studying how their light has shifted. Most galaxies show redshift. Because the universe is expanding and they're drifting away from us, the farther away, the faster the retreat, exactly as Hubble's law describes. But a few nearby galaxies, like Andromeda, actually show blue shift because they happen to be moving toward us instead. Andromeda, also called M31, is the nearest large galaxy to our own, sitting about 2.5 million light-years away, roughly 15 quintillion miles. It's approaching us at about 68 miles per second, or roughly 244,800 miles an hour. 68 miles a second might not sound especially fast compared to some of the numbers we've already covered. Earth orbits the Sun at about 18.5 miles per second, and the Sun circles the galaxy at around 136 miles per second. But here's the crucial difference. Andromeda isn't orbiting us. It's heading directly our way, with no sideways drift to carry it past us. It's on a genuine collision course. Roughly 4 billion years from now, give or take a few 100 million, Andromeda and the Milky Way will collide. That might sound sudden and violent, two entire galaxies smashing together at hundreds of thousands of miles an hour, but On any human timescale, this is an almost impossibly slow, gentle event. 4 billion years is a staggering length of time. That long ago, Earth had only just cooled enough to hold liquid water, and life was only beginning to stir, simple single-celled organisms drifting in the oceans. Multicellular life wouldn't appear for another 3 billion years after that. All of human history spans roughly 300,000 years, so 4 billion years is more than 13,000 times longer than everything humans have ever done or witnessed. The collision, in other words, lies impossibly far ahead of us. But it will happen. The evidence is solid. Andromeda's blue shift confirms it's approaching, and careful measurements of its sideways drift against background galaxies show it isn't going to slip past us. The trajectory points toward a direct meeting. There might even be a near miss on the very first pass, with the two galaxies swinging past one another, gravitationally warping each other's shapes, before swinging back for a second encounter, and then a third, gradually merging fully over time. Computer simulations have modeled this whole sequence, and the resulting animations are genuinely stunning to watch. Two enormous spiral galaxies drift toward one another, their graceful arms beginning to twist and stretch as they close the distance. Tidal forces, the very same forces behind ocean tides here on Earth, pull long streamers of stars out into open space. Eventually the galaxies pass right through one another, their stars intermingling. But here's the remarkable part: despite containing so many stars, actual collisions between individual stars are almost vanishingly rare. The Milky Way holds roughly 200 billion stars, and Andromeda about 1 trillion, yet galaxies are, in truth, mostly empty space. The average distance between stars in our stellar neighborhood is about 4 light-years, some 25 trillion miles, while a typical star measures only about 1 million miles across like a single grape, somewhere within a region the size of an entire continent. When two galaxies merge, their stars mostly just glide past one another undisturbed. The odds of any two stars actually striking each other are essentially zero. So if the Sun and Earth are still around in 4 billion years, which is uncertain for entirely different reasons, they would likely pass through the collision completely unscathed. The night sky, though, would look dramatically different. As Andromeda draws nearer, it will appear ever larger overhead. Right now it already spans about 6 times the width of the full moon in the sky, though it's so faint that you need genuinely dark skies to spot it without a telescope. As the distance closes, it will brighten and swell until it eventually stretches across half the visible sky, a vast glowing band overhead. During the actual merger, the sky would fill with stars from both galaxies at once, and new stars would form at an extraordinary rate, since gas clouds, unlike stars, really do collide and compress when galaxies merge. And compressed gas collapses under its own gravity to birth new stars. The result would be a dazzling burst of star formation, a sky ablaze with young, bright stars and glowing gas clouds. There's also risk buried in all this beauty, though the collision would tear apart the spiral structure of both galaxies, flinging some stars out into deep intergalactic space. Simulations suggest something like 10 to 20% of all stars could be ejected from the merged galaxy entirely. If the sun happened to be one of them, it would drift off into the emptiness between galaxies. The night sky from Earth would go almost entirely dark. No Milky Way, no Andromeda, only the sun, its planets, and a quiet black sky stretching in every direction. The nearest stars now millions of light years away and invisible to the naked eye. Lonely, certainly, but the sun and Earth would simply continue on, drifting through that emptiness. Or, just as plausibly, the sun might remain safely within the newly merged galaxy. Either way, the eventual result is a brand new galaxy, the two spirals fusing into one large elliptical galaxy, a more rounded, blob-like shape without the familiar spiral arms, composed mostly of older stars, with star formation largely finished. Astronomers have already given this future galaxy a nickname, Milkomeda, blending Milky Way and Andromeda. It's expected to hold around 1.2 trillion stars, and it will keep drifting through space, pulled onward by the gravity of distant cosmic structures. Now, you might wonder if the universe is expanding, pushing galaxies apart. Why aren't the Milky Way and Andromeda simply drifting away from each other too? The answer is that they're gravitationally bound together, close enough that their mutual pull is stronger than the stretching of space between them. They belong to the same local group of galaxies, roughly 50 galaxies in total, most of them quite small, held together by gravity. Expansion is happening everywhere, but on this local scale, it simply isn't strong enough to overcome gravity's grip. On far larger scales, expansion wins, and galaxies outside our local group are steadily carried away. But within the group itself, gravity remains firmly in charge, which is exactly why Andromeda keeps approaching, and why this collision remains on track, unless something we haven't yet accounted for changes the picture. There's another subtle effect worth mentioning, called aberration. Because Earth is moving through space, the direction we perceive starlight coming from is slightly different from the star's true direction. It's a bit like how rain seems to slant toward you when you're walking, even if it's actually falling perfectly straight down. Stand still in the rain, and it falls straight from above, so you hold your umbrella directly overhead. Start walking forward, though, and the rain appears to angle in from ahead, not because the rain changed course, but because you're moving into it, so you tilt your umbrella forward to compensate. The faster you walk, the more you have to tilt it. Starlight behaves in essentially the same way. Because stars sit at such vast distances, their light arrives in effectively parallel rays. But since Earth is moving through space, we're constantly moving into that incoming light, and from our perspective, it appears to arrive from slightly ahead of our direction of travel. This is called stellar aberration, and it was first observed by James Bradley back in 1728. Bradley had actually set out to detect something else, entirely stellar parallax. The tiny apparent shift in a star's position caused by Earth's orbital motion around the Sun. A purely geometric effect where the closer a star is, the larger its apparent shift. While observing a star called Gamma Draconis in search of this parallax, Bradley noticed the star's position did shift but in the wrong direction and on the wrong timing to match parallax. After careful thought, he realized he was witnessing something new. The star's apparent position was shifting because Earth's velocity kept changing direction as it swept around the Sun. When Earth moves toward a star, that star appears to sit slightly ahead of its true position. When Earth moves away, the star appears to lag slightly behind. When Earth's motion runs perpendicular to the star's direction, the shift reaches its maximum, and the whole pattern rotates through the year as Earth's velocity vector turns. Bradley measured this aberration angle at about 20.5 arcseconds, less than 0.006 degrees, an almost impossibly small shift, yet still measurable with the telescopes of his era. From this angle, combined with Earth's known orbital speed, Bradley was able to work out the speed of light itself, one of the earliest genuinely accurate measurements ever made. The aberration angle depends directly on the ratio between Earth's orbital speed and the speed of light Earth moves at roughly 5 miles per second, while light travels at about 186,000 miles per second, a ratio of roughly 1 to 10,000, which works out neatly to an aberration angle near 20 arcseconds. This discovery mattered for more than just measuring light speed. It also offered direct proof that Earth itself is in motion. Before Bradley's observation, the heliocentric model proposed by Copernicus still faced real skepticism, with some still holding that the Sun circled Earth rather than the other way around. But stellar aberration only makes sense if Earth is moving. If Earth sat perfectly still while the Sun orbited around it, there would be no aberration at all. Stars would hold fixed positions year-round. Instead, their positions shift in a pattern that lines up exactly with Earth's orbital motion, offering some of the earliest direct evidence that the Copernican model was correct all along. Every single star in the sky experiences this same aberration, though the size and direction of the shift depends on where the star sits relative to Earth's orbital plane. Stars near the ecliptic show the largest aberration. Stars near the ecliptic poles show far less. Modern telescopes must correct for this constantly. The Hubble Space Telescope, for instance, has to account for aberration when aiming at distant galaxies. Without the correction, it would point slightly off target. The error involved is only about 20 arcseconds, but at Hubble's level of precision, that's more than enough to matter. The European Space Agency's Gaia spacecraft faces this challenge too, in an even more demanding way. Gaia is mapping the positions of over 1 billion stars across the Milky Way with staggering precision, down to micro-arcseconds, millionths of a single arcsecond. At that level of detail, Gaia has to correct not only for Earth's orbital aberration, but for the Sun's own motion through the galaxy as well, which moves at roughly 155 miles per second relative to nearby stars, about 560,000 miles an hour. This creates an aberration effect roughly twice as large as the one caused by Earth's orbit, and Gaia must account for it carefully to determine truly accurate stellar positions. By measuring how those positions shift over time, Gaia can then work out the actual velocities of stars moving through the galaxy, creating, in effect, the most detailed map ever made of the Milky Way's structure and motion, revealing how the galaxy rotates, how stars drift through it, and how spiral arms form and dissolve across time. All of this made possible because we can measure aberration with such extraordinary precision. Aberration, in the end, is direct evidence of our own motion through space, and by studying it closely, we can work out exactly how we're moving. Let's turn gently to the subject of time, because motion affects it too. According to Einstein's special relativity, Time runs a little slower for anything moving relative to you, a phenomenon called time dilation. The faster the motion, the more pronounced the slowing, though the effect only becomes noticeable near the speed of light. At the ordinary speeds of daily life, it's almost immeasurably small. Let's work through it for Earth's own motion. Earth orbits the Sun at about 66,600 miles an hour, which converts to roughly 18.5 miles per second. Light travels at about 186,000 miles per second, meaning Earth's orbital speed is only about 0.01% of light speed, a mere 1 part in 10,000. At that pace, the time dilation factor sits almost exactly at 1. Worked out precisely, time on Earth runs slower by about 5 parts in 10 trillion. If you spent 1 full year on Earth while someone in a perfectly stationary frame watched, they'd measure your year as shorter by roughly 5 nanoseconds, 5 billionths of a second. Utterly unnoticeable across an entire human lifetime, let alone a single year. Even the Sun's own motion through the galaxy at 490,000 miles an hour works out to only about 0.07% of light speed. The time dilation there is still negligible, around 3 parts in 100 million. Meaning a year spent moving at the Sun's galactic pace would leave you younger by roughly 1/1,000,000th of a second compared to someone at rest. Still nothing a person could ever notice. You'd need to be moving at a genuinely significant fraction of light speed, somewhere around 10% or more, before time dilation starts to matter. At 10% of light speed, time runs about 99.5% as fast as normal. A year of travel at that pace would leave you roughly 2 days younger than someone who stayed home. At 50% of light speed, the gap widens considerably. Time runs at about 87% of its normal pace, meaning a year of travel would leave you about 7 weeks younger. At 90% of light speed, things shift dramatically. Using the relativistic time dilation formula, the factor works out to roughly 2.3, meaning time for the traveler runs about 2. 3 times slower than for someone at rest. A year for the traveler corresponds to roughly 2.3 years back home. At 99% of light speed, that factor grows to about 7 a year for the traveler, equals roughly 7 years for everyone else. At 99.9%, the factor reaches about 22. 1 year aboard the ship equals 22 years on Earth. And at 99%, the factor climbs to around 70. A single year for the traveler corresponds to 70 years back home. This is, remarkably, how time dilation could someday make interstellar travel possible within a human lifetime. A spacecraft moving at 99.9% of light speed could reach a star 10 light-years away in just over 10 years, as measured from Earth. But for the crew aboard, the journey would only feel like about 5 months, since their own time would be running 22 times slower. They could, in principle, travel to distant stars and return within a single lifetime, though everyone they left behind on Earth would have aged decades in the meantime. They would, in effect, be traveling into Earth's future. This isn't speculation or science fiction, it's a direct prediction of Einstein's equations, and it's been confirmed repeatedly using particles and accelerators. Muons offer a striking real-world example. These unstable particles form when cosmic rays strike the atmosphere roughly 10 miles up, and they hurtle downward at close to light speed. But muons decay quickly, with a half-life of about 2. 2 microseconds, meaning that even moving at light speed, a muon should only travel about 2,000 feet, less than half a mile before decaying. Muons born 10 miles up shouldn't reach the ground at all. And yet we detect them constantly at sea level. The explanation is time dilation. Muons travel at roughly 99.9% of light speed, and at that pace. Time runs about 22 times slower for them, from our perspective stretching their apparent half-life to about 49 microseconds, plenty of time to cover 10 miles and reach the surface. From the muon's own point of view, its internal clock ticks along normally at 2.2 microseconds, but the 10-mile distance to the ground appears contracted to less than half a mile, letting it complete the journey well within its brief lifetime. Both explanations are correct. They're simply two equally valid descriptions of the very same relativistic effect, verified again and again inside particle accelerators, where particles moving near light speed consistently live far longer than their stationary counterparts, exactly as Einstein's equations predict. In principle, the very motion we've been discussing tonight, the Milky Way's million-mile-an-hour drift through space, could in theory produce measurable time dilation if you somehow left that reference frame and returned. But the effect would be far too small to ever detect. At 1 million miles an hour, we're talking about only 15% of light speed, giving a time dilation of roughly 2 parts in a million. A year spent at that speed would leave you about 1 minute younger than someone stationary measurable with an atomic clock, perhaps, but utterly beyond anything a human being could perceive. To reach a dilation that actually matters in practice, you'd need speeds of 10 or 20% of light speed, and that demands staggering amounts of energy. Kinetic energy grows with the square of velocity, so doubling your speed quadruples the energy required. And as you approach light speed, things worsen further still. Relativity tells us that an object's effective mass increases the faster it moves, so the closer you get to light speed, the more energy it takes just to accelerate a little further. At 99.9% of light speed, your effective mass has grown to 22 times its resting value, meaning it takes 22 times as much energy just to push a little faster. As you approach light speed ever more closely, effective mass climbs toward infinity, and the energy required to actually reach light speed becomes infinite as well. This is precisely why nothing with mass can ever quite reach light speed. Only massless particles like photons can travel at that limit, while everything else remains forever confined to something a little slower. No matter how powerful the engine, you can creep closer and closer, 99%, 99.9%, 99,099%, but never quite arrive. And the nearer you get, the more energy each further increment demands. A 1-ton spacecraft trying to reach 99% of light speed would require energy equivalent to about 100 million tons of matter converted perfectly into energy, something we don't yet know how to achieve, and something well beyond current chemical rockets and even nuclear fusion. It would take some genuine breakthrough, perhaps antimatter propulsion, perhaps fusion ramjets scooping up interstellar hydrogen as fuel, or perhaps some idea we haven't even conceived of yet. Let's consider gently how all this motion touches our everyday lives. Does it actually matter to us in any practical way? As it happens, yes, in small but meaningful ways. Take GPS to begin with. The global positioning system depends on a constellation of 31 satellites orbiting Earth at any given moment, circling at an altitude of about 12,550 miles and completing one orbit roughly every 12 hours. These satellites move at about 8,650 miles an hour relative to Earth's surface. At that speed, time dilation becomes small but genuinely measurable. Special relativity tells us that moving clocks run slower, so the satellite's onboard clocks tick a little slower than clocks on the ground by about 7 microseconds per day. Not much, perhaps, but enough to matter. There's a second effect working in the opposite direction, though. The satellites sit in a weaker gravitational field than we experience on Earth's surface. And general relativity tells us that clocks in weaker gravity actually run faster. It sounds counterintuitive, but it's been verified repeatedly. Clocks at higher altitudes genuinely do run faster than clocks at sea level, if only by a tiny margin. For satellites orbiting 12,000 miles up, this effect speeds their clocks by about 45 microseconds each day relative to clocks on Earth's surface. So you have two competing effects: special relativity slowing the satellite clocks by about 7 microseconds daily, and general relativity speeding them up by about 45 microseconds daily. They partly cancel, but not entirely. The net result is that satellite clocks run about 38 microseconds per day faster than clocks down here on the ground. That might sound trivial, just 38 millionths of a second, but GPS works by precisely timing how long radio signals take to travel from satellite to receiver, and those signals move at the speed of light, roughly 186,282 miles per second. In 38 microseconds, light covers about 7 miles. So if GPS satellites didn't correct for these relativistic effects, your calculated position would drift by about 7 miles, and that error would only compound. After one day, 7 miles off. After 2 days, 14, within a week, GPS navigation would be effectively useless, placing you in an entirely different city than the one you're actually in. So GPS satellites are engineered to constantly correct for these relativistic effects born from motion and gravity. Their clocks deliberately run a little slower than they naturally would, precisely compensating. Every single time you check directions on your phone, you're quietly relying on corrections rooted in Einstein's theories. Without them, GPS simply wouldn't function. It's one of the most concretely practical applications of relativity in modern life. Most people imagine relativity as something abstract, relevant only to black holes and the Big Bang. But it matters every time you glance at a map app, every time a delivery truck finds your address using satellite coordinates. All of it depends on understanding how motion through space bends the passage of time. The engineers who built GPS had to account for Earth's rotation at over 1,000 miles an hour at the equator, the satellite's own motion at over 8,000 miles an hour, and the curvature of space-time caused by Earth's mass. All of it is quietly baked into the system, and it works. GPS is typically accurate to within about 16 feet under normal conditions, with some specialized systems achieving accuracy down to mere inches, all because we understand how motion shapes time. Second, there's cosmic radiation to consider. Earth is constantly bombarded by high-energy particles arriving from deep space, mostly protons moving at speeds close to light itself, some reaching 99.99% of light speed or beyond. They originate from supernova explosions, neutron stars, black holes, and other violent cosmic events, some from within our own galaxy, some from far beyond it, and perhaps a few tracing all the way back to the Big Bang itself. When these cosmic rays strike Earth's atmosphere, they trigger cascades of secondary particles. A single high-energy cosmic ray can spawn thousands, even millions, of secondary particles raining gently down toward the surface. Roughly 10,000 cosmic ray particles strike every square meter of Earth's surface every single minute. Dozens are passing quietly through your own body this very second. Most pass through harmlessly, since your body, at the atomic level, is mostly empty space, letting particles zip through undisturbed. A few, though, can damage DNA and potentially raise cancer risk. The danger at ground level stays low, thanks to 2 layers of protection. First, Earth's magnetic field deflects a great many cosmic rays, guiding charged particles along its field lines toward the poles, which is exactly why the aurora borealis and aurora australis appear near the Arctic and Antarctic. Those glowing curtains of light created by cosmic rays striking the upper atmosphere. Second, the atmosphere itself absorbs a great deal more. At sea level, roughly 10 tons of air sit above every square meter, and cosmic rays colliding with air molecules trigger cascading showers of particles that steadily lose energy as they fall. By the time anything reaches the ground, most of that original energy has already been absorbed, though a little still gets through. If you happen to fly in an airplane, you're exposed to noticeably more cosmic radiation. At typical cruising altitude, around 35,000 feet, there's only about 3 tons of air above you instead of 10, and radiation levels run roughly 100 times higher than at sea level. Pilots and flight attendants who log thousands of hours aloft receive measurable radiation doses over their careers, nothing dangerous for the occasional traveler, but something airlines and aviation regulators do monitor. Astronauts face considerably higher exposure still. The International Space Station orbits about 250 miles up, where there's almost no atmosphere left and the magnetic field grows weaker, exposing astronauts to radiation doses roughly 150 times higher than people on the ground. Over a 6-month stay, an astronaut absorbs about as much radiation as a full-body CT scan every 5 or 6 days, manageable for shorter missions, but a real concern for longer ones. Mars poses an even steeper challenge, since it has no global magnetic field and barely any atmosphere at all, with surface pressure less than 1% of Earth's. Astronauts traveling to Mars, a journey of roughly 6 to 9 months each way, would face the full brunt of cosmic radiation with little more than their spacecraft's hull for protection. And a round trip would likely deliver enough radiation to noticeably raise cancer risk. The faster we travel through space, the more of these high-energy particles we encounter, and there's simply no way to avoid them entirely on any mission to Mars or beyond. We could shield spacecraft with thick walls of water or plastic, materials rich in hydrogen that are especially good at stopping cosmic rays. We could generate magnetic fields to deflect incoming particles, effectively building an artificial magnetosphere around the ship. We could shorten mission durations to limit total exposure. Or, quite simply, we could accept the risk and go anyway, fully aware of what we're taking on. This remains one of the true challenges of long-duration spaceflight, not air, water or food, which are largely solved engineering problems, but cosmic radiation. A genuine consequence of motion through space that we can only partly mitigate, never entirely erase, so long as we keep traveling through the galaxy at hundreds of thousands of miles an hour. Third, there's the cosmic microwave background itself. Because we're moving relative to it at over 1,000,000 miles an hour, the CMB appears slightly warmer in the direction we're heading and slightly cooler in the opposite direction. This dipole anisotropy is, in fact, how we measure our own motion through space in the first place. It also means the universe looks subtly different depending on which way you look. This has no real effect on daily life, but it matters greatly to cosmologists, who must carefully subtract this dipole pattern out of their data whenever they study the CMB to understand the early universe, revealing the deeper structure hidden beneath our own motion. And fourth, there's the expansion of space itself. This expansion doesn't touch us locally, since gravity holds the solar system firmly together, but on the grandest scales, it reshapes the entire universe. Galaxies billions of light years away are steadily receding from us, their light stretched into redshift, and because of that expansion, we can actually observe galaxies that now lie beyond our current cosmic horizon. Their ancient light, emitted billions of years ago when they were much closer, is only now arriving, even though the expansion has since carried them beyond where any future light could ever reach us. We're seeing them as they once were, never as they are now. And we never will, because their present light will never make the journey to us. The observable universe is, in this sense, constantly shifting new light arriving from distant corners, even as older galaxies slip beyond the horizon forever. The universe we witness isn't the universe as it exists today, but a patchwork of moments frozen at different points in the deep past. And every bit of this, ultimately, traces back to motion through space, and the motion of space itself. Let's drift for a moment into something a little more philosophical. What does all this motion mean for our place in the universe? For most of human history, we assumed we sat at the very center of everything Earth motionless, with the sun, moon, and stars all wheeling around us, ourselves the fixed point around which the whole cosmos turned. It made intuitive sense, standing on the ground and watching the sky appear to rotate overhead. This geocentric picture held for thousands of years, until Copernicus demonstrated that Earth instead orbits the Sun, publishing his model in 1543 and placing the Sun at the center, with Earth demoted to just another planet. It was a revolutionary claim, one the Church resisted for centuries, but the evidence steadily mounted in its favor. Then we discovered that the Sun itself is merely one star among billions scattered across the Milky Way. We weren't at the galaxy's center either, but tucked out in its quieter suburbs, roughly halfway between the core and the edge. Nothing special about our particular address. Later still, we learned the Milky Way is just one galaxy among trillions filling the observable universe, not the center of the universe either, because the universe, as it turns out, has no center at all. The Big Bang unfolded everywhere at once, and every point in space is equally valid as the origin of that expansion. And now we know that we're moving through space at over 1,000,000 miles an hour, gently pulled by gravity toward vast structures we can barely glimpse. We're not at the center of anything. We're not standing still. We're simply one modest planet, in one modest solar system, within one galaxy among trillions, all drifting through an ever-expanding universe. This idea is sometimes called the Copernican principle, the notion that there's nothing uniquely privileged about our location or our motion, that we are, in the broadest cosmic sense, entirely ordinary. And in a way, that's genuinely humbling. It puts us gently in our place, reminding us that the universe doesn't literally revolve around us, that we aren't the central characters in some grand cosmic story, but simply observers quietly trying to make sense of what surrounds us, small beings on a small planet, gazing upward at a vastness that dwarfs us, wondering what any of it means. But there's another way to see it. Yes, we're small. Yes, we're hurtling through space at extraordinary speed. Yes, we occupy no special position in the cosmos. And yet, as far as we know, we're also the only beings capable of understanding any of this. We're the only ones who can measure the cosmic microwave background and work out our own motion through space from it. We're the only ones who can build telescopes powerful enough to glimpse galaxies billions of light years distant. We're the only ones who can piece together the fact that we're moving at over 1 million miles an hour and then explain, calmly, why we can't feel it. We're the only ones who can sit quietly and wonder about our own place in the universe. That in itself feels remarkable, worth considering, at least. Out of every planet, in every galaxy we know of, Earth is the one that gave rise to a species capable of asking these questions, and, slowly, patiently, finding some of the answers. We might not sit at the center. We might not be standing still. But we're conscious. We're curious. We're capable of wonder. And that makes us special in an entirely different sense, not because of where we happen to be, but because of what we're able to do. We can think, question, explore, and understand. We're built from atoms forged inside the hearts of long-dead stars, and in a very real sense, we're the universe's own quiet way of coming to know itself. Through us, unthinking matter has somehow become aware. That, quietly, is a profound thing to sit with. So let's return gently to the question we began with tonight. How fast are we really moving through space? And the honest answer is, it depends entirely on what you mean by really. Relative to Earth's surface, you're barely moving, maybe a few miles an hour if you happen to be walking. Relative to Earth's center, you're moving at up to 1,040 miles an hour, thanks to its rotation. Relative to the Sun, you're moving at about 66,600 miles an hour. Relative to the galactic center, roughly 490,000 miles an hour. And relative to the cosmic microwave background, about 1,342,000 miles an hour. Every single one of those answers is entirely correct. They're simply measuring different things. There's no single true speed, because motion, as we've seen throughout tonight, is always relative. There's no absolute frame anywhere, no cosmic grid, no universal clock ticking away somewhere, only different perspectives, each equally valid in its own right. This was one of Einstein's deepest insights when he developed relativity. Motion is relative. Time is relative, even space itself is relative. What remains constant, unchanging for everyone regardless of speed, is the speed of light and the underlying laws of physics themselves. Speed, though, always depends on who's doing the measuring. So the next time someone asks how fast you're moving, you could honestly answer anywhere from 0 to over 1,000,000 miles an hour, and you'd be correct either way, depending entirely on your chosen frame of reference. Let's turn our attention gently toward the future. What becomes of all this motion as the universe continues its slow unfolding? First, Earth's rotation is gradually winding down. The moon's gravity raises tidal bulges on Earth, pulling most strongly on the side closest to it, less on Earth's center, and least on the far side. This uneven pull, called a tidal force, stretches the planet very slightly. Solid rock barely deforms, but the oceans respond far more noticeably, bulging toward the moon on the near side and, curiously, bulging outward on the far side too, since it's tugged less than Earth's center. So Earth carries two tidal bulges at once, and as the planet spins, different regions pass through them high tide when you're within a bulge, low tide when you're between them, which is why most coastlines experience 2 high tides and 2 low tides daily. But here's the key detail. Earth spins faster than the moon orbits. Earth completes a full rotation every 24 hours, while the moon takes about 27.3 days to circle us. So Earth constantly tries to drag its tidal bulges along as it spins, while the moon's gravity tries to keep them aligned with itself, and the friction between these competing pulls creates a subtle braking force. The bulges end up sitting slightly ahead of the Earth-Moon line, generating a torque that gradually slows Earth's spin, much like a very gentle brake. Friction between moving water and the ocean floor bleeds away rotational energy borrowed straight from Earth's own spin. The effect is tiny Earth's day lengthens by only about 1.7 milliseconds per century, an amount no human would ever notice in a lifetime. But across geological time, it accumulates meaningfully. About 600 million years ago, a day on Earth lasted only around 21.5 hours, back when the first complex multicellular life was just emerging in the oceans, with the planet spinning noticeably faster and years containing more, if shorter days. We know this from studying ancient coral growth rings, which, much like tree rings, record daily layers, letting paleontologists count how many days fit into a year hundreds of millions of years ago, and the data consistently shows shorter days and more of them per year. Going back even further to roughly 4.5 billion years ago when the moon first formed, Earth spun considerably faster. Still, a day may have lasted only 4 or 5 hours. The moon itself sat much closer too, about 15,000 miles away compared to today's roughly 239,000 miles, meaning it would have loomed enormously in Earth's sky, some 15 times larger than it appears now, driving tides that reached hundreds of feet in places. Over the billions of years since, two connected changes have unfolded together. Earth's spin has slowed, and the moon has drifted steadily farther away. As Earth loses angular momentum through its slowing rotation, that momentum doesn't simply vanish, it transfers to the moon, expanding its orbit in turn. The moon currently recedes from Earth at about 1.5 inches per year, roughly the same pace your fingernails grow. We know this with remarkable precision because Apollo astronauts left small reflective devices on the lunar surface, and scientists on Earth bounce lasers off them, timing the return trip to measure the moon's distance to within a few millimeters. Looking ahead, Earth's spin will keep slowing, and the moon will keep drifting outward. Eventually, billions of years from now, Earth's rotation will slow enough that one side permanently faces the moon, a state called tidal locking. At that point, a day on Earth will match the moon's orbital period, both stretching to roughly 47 of today's days. One hemisphere would always see the moon hanging motionless overhead, the other would never see it at all. This has in fact already happened to the moon itself. Its rotation slowed long ago until it became tidally locked to Earth, spinning once per orbit, which is exactly why we only ever see one face of it. The far side, often mistakenly called the dark side, receives just as much sunlight as the near side. It simply never faces us. The same fate awaits Earth eventually, though it will take far longer, since Earth is so much more massive than the moon that slowing its spin demands vastly more energy. And by the time Earth would reach that point, something else entirely will likely have already happened. The sun will have swollen into a red giant, quite possibly swallowing Earth whole, or at the very least scorching it beyond recognition. So Earth's rotation will probably end not through tidal locking at all, but because the planet itself will have been destroyed or rendered utterly uninhabitable. For now, though, Earth keeps spinning, slowing gently at 1.7 milliseconds each century, quietly losing rotational energy to the tides, while the moon drifts outward 1.5 inches each year, carried by momentum stolen from Earth's own spin. Second, Earth's orbit around the Sun is slowly shifting too. The Sun sheds mass constantly through fusion and solar wind, roughly 4 million tons converted into pure energy every second. As the Sun loses mass, its gravitational grip weakens very slightly, and Earth's orbit gradually spirals a little farther outward by about 1.5 centimeters a year, less than an inch. Over billions of years, though, this quietly accumulates, and Earth may end up considerably farther from the Sun than it sits today, which might actually spare it from being fully swallowed when the Sun eventually swells into a red giant, expanding to roughly 250 times its current size, a reach that would currently extend just past Earth's orbit. By the time that expansion happens, Earth may have drifted just far enough to avoid being engulfed outright, though it would still be thoroughly scorched, its oceans boiled away, and its atmosphere stripped, surviving perhaps only as a barren husk orbiting what remains a white dwarf star. Third, the Sun's long orbit around the galaxy will simply continue. Over the next 4 billion years, it will complete roughly 17 more full circuits, each lasting about 230 million years. But the galaxy itself won't stay the same. Stars will keep forming and dying, supernovae will scatter heavy elements outward, and new solar systems will condense from the debris. Eventually, of course, the Milky Way will merge with Andromeda, and when that happens, the Sun's own orbit will be thoroughly disrupted. The newly merged galaxy will have an entirely different structure, and the Sun might end up somewhere else within it entirely, or possibly be flung out into intergalactic space altogether. We simply don't know, but the collision will reshape everything. Fourth, the galaxy's motion relative to the cosmic microwave background will keep unfolding. The Milky Way will continue falling toward the Great Attractor, continue moving through space at well over 1,000,000 miles an hour, and will eventually merge with the other galaxies of our local group, the Milky Way, Andromeda, and their smaller neighbors, all fusing into one enormous elliptical galaxy that astronomers have already nicknamed Milkomeda, larger than either galaxy alone, continuing its journey pulled ever onward by the gravity of far more distant structures. And fifth, the expansion of the universe itself will continue, and it's accelerating. This remains one of the more profound discoveries in modern cosmology. For most of the 20th century, scientists assumed the universe's expansion was gradually slowing, since gravity should be pulling everything back together after the initial outward burst of the Big Bang. The open question was simply whether there was enough matter to eventually halt the expansion and trigger a big crunch, a reversal collapsing everything back together, or whether expansion would continue forever, just gradually easing. In the late 1990s, two independent teams of astronomers set out to measure exactly how much the expansion was slowing, studying Type I supernovae stellar explosions bright enough to be seen across billions of light years and remarkably consistent in their intrinsic brightness, meaning a dimmer one simply sits farther away. By carefully measuring both the brightness and redshift of these distant explosions, researchers could work out both distance and recession speed, revealing how the expansion rate had shifted over cosmic time. Both teams expected to find a slowing expansion. Instead, they found the very opposite distant supernovae appeared dimmer than expected, meaning farther away than expected, meaning the universe had expanded more than anyone had predicted. The expansion rate was increasing, not decreasing. This result was genuinely shocking, upending decades of assumptions. Both teams rechecked their work repeatedly, hunting for errors, weighing alternative explanations, but the data held firm. The expansion of the universe truly is accelerating. In 2011, the three lead researchers, Saul Perlmutter, Brian Schmidt, and Adam Rees, received the Nobel Prize in Physics for this discovery. But the finding raised an enormous question. What could possibly be driving that acceleration? Gravity pulls things together, it can slow an expansion, but it can't speed one up. Something else, some other force, must be pushing space apart, and scientists have taken to calling that something dark energy. A name that's really more placeholder than explanation, simply acknowledging that some form of energy is behind the acceleration, without yet knowing what that energy actually is. The simplest explanation treats dark energy as an inherent property of space itself. Einstein's own equations include a term called the cosmological constant, which he originally introduced to keep the universe perfectly static, neither expanding nor collapsing, a choice he later called his greatest blunder, once Edwin Hubble discovered the universe actually was expanding. And yet, it now appears the cosmological constant may have been onto something real after all, representing the intrinsic energy density of empty space itself. Even seemingly empty space, according to quantum field theory, isn't truly empty at all. It churns with quantum fluctuations, virtual particles flickering briefly into and out of existence, and these fluctuations lend the vacuum a small but genuine energy. If empty space carries energy and the universe is overwhelmingly empty space, then the total vacuum energy grows as the universe expands. More space simply means more vacuum energy, which in turn pushes space apart still further, accelerating the expansion in something of a runaway feedback loop. There is, admittedly, one significant wrinkle in this explanation. When researchers calculate vacuum energy using quantum field theory, the predicted value comes out roughly 10 to the power of 120 times larger than what we actually observe, a 1 followed by 120 zeros, arguably one of the worst mismatches between prediction and observation in the history of physics. Nobody yet knows why the calculated figure diverges so wildly from reality, a puzzle known as the cosmological constant problem, and one of the deepest unsolved mysteries in modern physics. Despite that unresolved tension, the simplest model that actually fits our observations involves a cosmological constant with a very small positive value. Roughly 68% of the universe's total energy content comes from dark energy, another 27% from dark matter, and only about 5% from ordinary matter, the atoms making up stars, planets, gas, dust, and everything we can actually see. All the visible universe amounts to just 5% of the whole. The rest remains genuinely dark, its nature still unknown. Unlike matter, dark energy doesn't clump together, it spreads uniformly through space, and its density stays constant even as the universe expands, which is exactly why it becomes more dominant with time. As the universe grows, ordinary matter becomes ever more diluted. Galaxies drift farther apart, and matter's average density steadily falls. Dark energy's density, though, holds steady, so as the universe grows larger, dark energy makes up an ever larger share of the total until eventually it dominates completely. This acceleration has been underway for roughly the last 5 billion years. Before that, the universe's expansion was actually decelerating, gravity's pull still dominant. But as expansion continued and matter grew more dilute, gravity's influence weakened while dark energy's influence held steady, or perhaps even grew until, at some point, dark energy took over entirely, and the expansion began speeding up. Looking far into the future, this acceleration will only continue. Distant galaxies will be pushed beyond our cosmic horizon, and the observable universe will steadily shrink, not because the universe itself is getting smaller, but because light from ever more distant galaxies will simply never reach us again, carried away by expansion faster than light could ever travel toward us. Eventually, over trillions of years, the only galaxies still visible will be those gravitationally bound within our own local group, the Milky Way, Andromeda, and a handful of smaller companions. Everything else will have drifted entirely beyond view, carried off by the relentless stretching of space. A hypothetical observer in that distant future would look up and see only their own galaxy, perhaps a few close neighbors if any remain unmerged, but nothing more. They would never see the cosmic microwave background, its light stretched by then into complete invisibility, its wavelength drawn out toward infinity. They would have no evidence at all that the universe was ever expanding. No way to detect the Big Bang, no way to measure the universe's true age. All the evidence available to us tonight would have simply faded from their view entirely, leaving them to assume their own galaxy was the whole of existence, utterly alone. We happen to be living in a genuinely special moment, old enough that stars, galaxies, and intelligent life have all had time to emerge, yet young enough that the deep evidence of the Big Bang remains visible to us. We can still observe distant galaxies. We can still measure the expansion directly. We can still detect the cosmic microwave background glowing softly across the sky. Far in the future, none of that will remain possible. The evidence will simply have vanished, and any civilization arising after us will be cut off from truths we can still access today, unless somehow, some way, we manage to leave word of them behind. That makes this era of ours quietly unique, not merely within human history, but within the entire history of the cosmos, a brief window during which the universe's deepest secrets remain visible to those curious enough to look. So all this motion, every one of these staggering speeds, is part of a universe in constant, restless change. Earth is moving, the sun is moving, the galaxy is moving, and the universe itself continues to expand. Nothing holds still, nothing lasts forever unchanged. Everything is in motion, and everything continues to change. So, quietly, what have we gathered tonight? We've learned that you are, at this very moment, moving through space at more than 1,000,000 miles an hour. We've learned that this motion comes layered, one on top of the other. Earth's rotation, Earth's orbit, the sun's orbit, the galaxy's own motion, and the gentle expansion of space, all unfolding together, all at once. We've learned that none of it can be felt, because it's smooth, steady, and shared entirely with everything around you. We've learned that motion is relative, that there's no single true speed, only speed measured against something else. We've learned how this motion shapes the way we see the universe, how we find our way through space, and even how we measure the passage of time itself. And we've learned that all of it will keep gently changing across billions of years as the universe continues its long, quiet evolution. But here's the most important thing of all. None of this motion changes your daily life in the slightest. You're sitting still relative to your surroundings, and that's really the only motion that matters for how you experience the world moment to moment. The fact that you're hurtling through the cosmos at extraordinary speed doesn't alter a single thing about how you live. You're still you. You're still here. You're still experiencing everything exactly the way you always have. And yet, knowing about this motion, understanding it even a little, does change something quietly important. It reshapes how you see yourself within the larger sweep of the universe. It's a gentle reminder that you're part of something vast, dynamic, endlessly in motion, not separate from the universe at all, but woven into it. You're riding on a planet which is riding within a solar system, which is riding within a galaxy, drifting through an ever-expanding universe, connected in a quiet way to absolutely everything. Every atom inside you was forged long ago in the heart of some star that lived and eventually died billions of years before you were born. Those atoms have been drifting through space ever since, circling the galaxy, collapsing into new stars, scattered outward in supernova explosions, eventually finding their way here, to Earth, and eventually becoming part of you. You are, quite literally, made of stardust, and you are moving through space right now at the very same staggering speeds as those ancient stars once did. You're not simply on Earth. You're on a journey, one that began billions of years ago and will continue long after you're gone. A journey through both space and time. And even though you'll never feel the motion, even though it seems right now as though you're sitting perfectly still, you remain part of this enormous, quiet, cosmic dance. And that's something worth sitting with for a moment. So the next time you find yourself somewhere quiet, perhaps at night, looking up at the stars, remember this: you are not still. You're moving faster than any car, any plane, any rocket ever built. You're moving through space at over 1,000,000 miles an hour, and you're doing it right now, this very second, every moment that passes. You're on the ride of a lifetime, and you never even had to buy a ticket. Thank you for spending this time with me, exploring motion together tonight. If this journey through the quiet mechanics of the cosmos gave you something to think about, it would mean a lot if you considered liking this video and subscribing to the channel. It genuinely helps me keep making these deep, unhurried dives into the universe. And remember, gently, as you drift off, you're not sitting still. You're moving through space at truly incredible speeds. You simply can't feel it. And that, quietly, is one of the more beautiful mysteries the universe has to offer. Sleep well tonight, knowing you're part of something vast and endlessly in motion. You're traveling through the cosmos at speeds that would make even the fastest rocket look slow by comparison. And tomorrow, when you wake, you'll have already traveled millions of miles through space, all while you were dreaming. The universe is in motion. And so, quietly, gently, are you. Good night.